before we get started on this tangent line problem that today is going to focus on, this is really a big problem, and calculus revolves a lot around this problem. Let's start with a little algebraic problem. Say you're going on a road trip with Grandma, and this is a graph showing what's happening as time passes. So we have our hours here. This is how many miles you've traveled. So as time passes, the miles increases. That makes sense. All right. If you were to find the slope of this particular line, that would be your rate of change. If you look at that, some nice notation. This is the change in y over the change in x. And so I picked these 2 points and I did my slope formula and I get 50. Now, your slope then is 50, and you have to recognize that that is your rate of change. It's your change in y. It's your miles over your change in time, so it's miles per hour. This 50 is actually your speed. When you find the slope, you're finding the speed. Here's the problem with that scenario is, if you've ever ridden with Grandma, it doesn't really work like that. Here's really what's going on. Grandma's driving. She's going 50 miles per hour. So you put up with that for a while, and then at some point you're like, Grandma, can I drive? And then you increase the rate, and so it's a little bit faster. Then, of course, Grandma's going to need a potty break, and so you're going to take a break here where your distance stays at 300 even though time is passing. And then she'll remember that her friend Dolores lives back in that town that you just went past, so she'll want to go back and visit Dolores for a little bit, but Dolores isn't home, so now you're going to keep going, and you are going to drive way faster because you're losing time now. All right, so that's really a more varied trip over a long span of time. Now, in real life, things don't typically happen quite so straight. Things happen in a more of a curve situation rather than in these straight segments. So this might be more like what a situation we're talking about is. And so in calculus, we talk a lot about curves. And we could find the average speed, because this is a lot of stuff was going on this road trip. I could find an average speed from here to here, the same way I did originally, but that of course would be for this straight line, and that's not really representative of what was going on. Mathematicians were trying then, okay, so instead of finding this average speed from start to finish, or even from here to here, and finding an average over that short little piece, Galileo was one of the mathematicians that was really in search of like an instantaneous velocity rather than an average velocity. Let's start off though and break this down, and let's look at the average velocity. And I'm not going to go start to finish. I'm just going to pick a chunk here where I have to go from here to here, and I realize I kind of was going slower, but you can see the slope starts to increase, so I was getting faster. I'm just looking for an average from here to here though. What was my average speed? All right, on the previous one, I had like ordered pairs I was using. Now what I want to look at is I want to look at this a little bit more generically. Don't think numbers that I'm plugging in here. I am going to create an ordered pair for this point and an ordered pair for this point, but I don't want it to be just numbers. I want you to look at what I've listed down here. Typically this is an x comma y, right? So I need the x value for this spot right here. Well, if you look down here, I'm just going to call it x for right now. The x value will be x, comma, and then the y value that would match that is whatever this y value would happen to be. And again, I'm not looking over here. Don't look over here. Just say, well, this is the y. And I'm going to put a y here, except I'm going to use some nice algebraic notation, and I'm going to call it f of x instead of calling it y. Now let's try it over here on this other ordered pair. This is not x anymore. This is a different x value. And we call this distance that we've traveled from here to here. And really that's not distance, that's the time that has passed. We're going to call that h. However far to get from here to here, it was h. So this x value isn't x, it's going to be x plus whatever h is. So I'll put in my ordered pair x plus h as my x value. And that means for my y value, instead of putting a y there, I would put the nice notation, but it's not f of x, because I used x because that's what it was. It'll be f of x plus h. Kind of fancy. Now what I'm going to do then is I could use my slope formula to find the slope of this line. I'm going to do the change in y. I'll take my y minus y, f of x plus h minus f of x, all over x minus x, x plus h minus x. Now look what's going to happen nicely. These x's are going to cancel, and I'm left with f of x plus h minus f of x all over h. And this right here is the formula for average velocity. Regardless of what the function is doing, this is how we would work that formula. Now that is all fine and dandy. That's great for average velocity. But ultimately, we are looking for instantaneous velocity, not an average velocity from here to here. I want to know at any particular moment, and we call this a secant line right here, because it crosses through a curve and it hits twice. That's a nice geometry term, the secant line. But what could I do with this secant line so that instead of finding an average from here to here, it's really just more of an instantaneous spot rather than having two? Well, you would have to take this secant line, and I can't really do it, but I'm going to nudge it down so that I'm going to pull this and this point closer and closer to one another. So maybe they need to go like scoot this one over to here and scoot this one over to here, and then I'd have that secant line. And that's better. I'm getting closer. That's not such a distance between my 2 points, but it's still going to end up being an average velocity. Well, the smaller, or that increment I make that, the closer this becomes to being instantaneously. Right now it's still average. If I got rid of that and I made those 2 points like super duper close, like that close, and then I draw the secant line, okay, now I'm going to have the slope of this secant line is going to be my average velocity, and it's really, really close to one another. What do you think is going to have to happen for this to actually ever end up being instantaneous? What do you think about my 2 points? Yeah. In order for it to be instantaneous instead of average, my 2 points need to be 1 point. Those two need to be touching each other. And then what is my secant line actually going to turn into then? A tangent line. The problem that I have is if I don't have 2 points, then how does this all work? Because I wouldn't have 2 points to do that formula with. Well, let's look at it. I have to treat this actually like a limit, because if I don't have 2 separate points, my 2 points are the same point, then what I'm really doing is I'm looking at this as this h, which is the distance between my 2 x's, right here, this h value down here. What I'm doing is I'm treating it like a limit, and I'm letting h, the distance between these 2 points, is approaching 0. And then I'm going to look at it. I'm going to use that previous formula, but I'm going to treat it as a limit as I do that. You can see in my picture that my secant line is now a tangent line. And I'm going to write this formula now, and this is now for instantaneous velocity. It is going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. The previous formula, which only had this part in it, was the slope of the secant line and was the average velocity. When I look at this as though it's a limit and include that as part of my formula, and so this is my new formula, that is going to be the slope of the tangent line, which is instantaneous velocity. Now I want to make sure that you have everything in your notes that we've been talking about. So here's a quick summary. Make sure you have this stuff in here. Average velocity is always going to be the slope of the the slope of the secant line. And it is going to be, the formula is f of x plus h minus f of x all over h. Now, instantaneous velocity is actually the slope of the tangent line. And that's why we call it the tangent line problem. That's this whole lesson is about. It's the slope of the tangent line. And that's such an important value. We actually have a name for that. It is called the derivative. So maybe you've heard of that from calculus, finding derivatives. Oops, messed that up. And it has a notation. When you find the derivative, we notate it as f with a little apostrophe thing here, f of x, like that. Or sometimes we call it dy dx. Either one of those notations means find the derivative, which means find the slope of the tangent line, which is, formula-wise, is similar to the average velocity, except that it is a limit now. It's the limit as h approaches 0 of f of x plus h minus f of x all over h. And then one special thing that we should probably chat about before we get too far, provided the limit exists. And so remember from our previous lesson that sometimes the limit doesn't exist, so we have to be careful. Real quick, let's talk about some points where we might be concerned about the derivative existing. If I have a scenario like this, I could be driving along or whatever I'm doing. This is fine. Right here, I could find the slope of this. And I could have, and really when I find the slope of the tangent line is going to land right on top of this. The problem that I'm going to have is right here. I could not find the instantaneous velocity right here because I don't know if this right here is my tangent line that just barely touches it, or if this is my tangent line, or if this is my tangent line. I have too many options for my tangent line. Anytime your graph, your function, turns around suddenly like that and has a point in it, that's going to provide a problem on finding the derivative. Okay, on this one, I could have like a tangent line right here, or maybe I'm talking about this spot and then my tangent line would look like that, or maybe this spot and my tangent line would look like that. The problem happens on this particular graph right here at 0, because think about what your tangent line is going to look like at that point. Well, it's going to end up vertical. And what is the slope of a vertical line? It's undefined. If the slope of your tangent line is undefined, if it happens to be a vertical tangent line, then the limit would not exist. And then the last situation that we would have trouble finding the derivative would be on this kind of thing, where, all right, I'm fine here, I could find the slope of this, but right here at x equals 0, I don't know whether to be using this piece of it or this piece of it up here. So if it jumps at the spot you're trying to find the instantaneous velocity, that's not going to work. So those are some special situations that might happen. Let's look and see if we can maybe try to estimate the derivative. So you're always thinking the derivative is the slope of the tangent line. Let's see if we can draw in a tangent line and estimate its slope on a graph. Now, I have a couple examples here. We've got this first graph, and I'm looking specifically at x equals 0. What that means is I need to draw the tangent line at x equals 0. I want my tangent line to hit this spot right here on the function at x equals 0 and just barely hit the function so that it's tangent right there. So coming in, hit that point, keep moving. And then I have to figure out what the slope of that line is. And I'm just going to count my rise and run on that. If I had to guess from this point, it looks like I went up 1 over 2. And I think that feels fairly consistent. So if I had to estimate it, I'd call it about 1/2. That doesn't have to be exact. You might have something different. That's okay. I'm going to say that the slope is about 1/2, and that's what the derivative would be. Okay, looking at this second example, I'm looking specifically at x equals 2. At x equals 2, that's right here at this spot. Ooh, that's one of those problem ones, isn't it? Because remember, you can't have the function have a point and just suddenly turn around. If you have like this spot where it turns around, then I can't determine the limit because I have options on what I could draw for a tangent line. It might be that, it might be this, I don't know. This would be no limit. No, or no derivative is what that is. Let's try one more. This one is a parabola, specifically at x equals 3. So at x equals 3, it looks like I land right here on my function. So my job is to draw the tangent line at that spot. This is going to be pretty steep, it looks like. I think it's going to come in here. Barely touch that spot and keep on going, keep on going, keep on going. Something like that. And I have to find the slope. Now I wish I had made my graph just a little bit bigger because I'm wondering, where's that look like that's maybe crossing? Is that, I don't know, not real pretty. So maybe find a different spot that it crosses nice. Maybe like right here. So from here to here, let's count our rise and run. So rise 1, 2, 3, 4, 5, 6, 7, run 2. So the slope of my tangent line or my derivative is 7/2. And as long as you're ballpark sort of close to that, you're going to be okay. Okay, let's go back to your notes for a little bit. Finding the exact derivative. We start our homework and we're just trying to estimate and kind of visualize what's going on. Ultimately, though, we're going to want some exact answers. Let's look at one. I'm going to give you a function this time. It's going to start off as a pretty simple function. It's just linear, x minus 2. And we're going to find the exact derivative using, and this is called, this formula that we're using, that we came up with earlier, this limit, that's called the difference quotient. And see how I have this written, and you'll see me write it like this a lot. You'll say the derivative is, right here's our notation for the derivative, and then we have to have the limit in there, and then we use this whole piece of the slope thing. That's the formula, the difference quotient that we'll be using. I'm going to start off, show some neat work here, because it gets harder, and so we want to kind of practice the skill of writing it nice as it's easy, so that when this function gets way crazier, and it will, then we'll kind of have the basics down. So I'm going to write the derivative is equal to, leave that limit in there. That's going to be important to keep the limit. Otherwise, it's just an average velocity. Now, to do f of x plus h, that means take x plus h and put it in for x. That's going to look like then, instead of x minus 2, it's going to be x plus h minus 2. And then I'm supposed to subtract the actual function. That means subtract, and then in parentheses, I'd have x minus 2. Now we're in PreCalc, so I'm going to do this one time, and then I'm done doing this. But if I subtract the function, notice that means I'm going to have to subtract both of those. So I'm going to start doing that in my head. I know that I'm going to end up, if I subtract this function, it's going to be minus x plus 2. It's going to change your signs. And this is all over h. Then we're going to try to evaluate the limit, so that means direct substitution usually. We're going to plug 0 in for h, but right away, and I hadn't pointed this out earlier, but do you see a problem with direct substitution? And since that's the formula, it's going to happen every single time that I have that issue. That means I'm hoping to get something simplified up here to where this h might divide out. Remember how we were factoring and doing stuff previously to try to get that h, or that denominator, to go away? Look at what happens on this problem. This positive x and this negative x are going to cancel. This positive 2 and this negative 2 are going to cancel. And I end up with h over h. Well, gosh, h over h is going to cancel also. And all of that, I don't even have anything to evaluate anymore. It just ends up equaling 1. the derivative is equal to 1. That's kind of weird. That is a weird one. I want you to come over here and look at the graph, though. Look at what you have. It's a line. It has a y-intercept of -2. It has a slope of 1. If this is my actual function, and I was going to draw a line tangent to it, at any place at all, it's just going to ride right along that line. It's going to be the same as the line. It'll have the same slope as the line. And what was the slope up here in my function? It was 1. This should make sense then that the derivative would match what the slope was on that line. Now that's a special case. That's because this happened to be a line. Let's try something harder. Now it's still not super hard, but I did at least make it a quadratic instead of a linear function. But I'm going to have to do some squaring, and that's going to get a little bit tricky. We're going to find the derivative, so nice notation. Start off and say the derivative is equal to, keep the limit in there because that's what makes it the instantaneous velocity. That's what makes it the slope of the tangent line. And then I'm going to have f of, and I take this x plus h and I plug it in right there. And I'm going to have x plus h squared. So I'm going to get rid of this f of x that I was writing, and I'm just going to write x plus h squared minus the function itself, so I'm just going to subtract the x squared. And then I'm going to have that all over h. Again, can't do the direct substitution, so I'm going to clean up the numerator and hope something will divide. Now, let's talk about something else that now that we're in pre-calc, I would expect you to be able to do. Let's talk about this x plus h squared. You might still be writing this out as x plus h times x plus h. I hope you are not distributing your squared because you can't do that. But you'd write it out, and look what happens. If you multiply the first, you're going to have x squared. But look at your outer and your inner. That's just x times h and another x times h. That will always happen where you're multiplying the same two values. That's going to be 2x plus, or 2, did I say x plus h? I meant x times h. I don't know what I said. 2xh. And then my last is going to be plus h squared. To square a binomial, we're going to just start doing, we're going to go from here to here. We don't have time to be doing FOIL because we're going to get some ugly functions, and we want to be able to do some of that in our head, some of that algebra you've been doing for years. You always just, okay, so here's what it boils down to. To square a binomial, you square the first term, you square the last term, and you multiply these two, and then always double it, because there will always be two of those exact same terms. So I'm going to go from here to here every time now. I'm going to clean this thing up. The derivative is the limit as h approaches 0 of, this is squared out, it can be x squared plus 2xh plus h squared minus x squared all over h. X squareds are going to cancel. Notice that everything that's left has an h. That means, remember, anything up here is being divided by h. These h's then could reduce, and these h's could then reduce. That one's going to go away. That's going to turn into a 1. The derivative is the limit as h approaches 0. And it looks like I have left a 2x plus h. Now, you have to kind of remember where we're at here. We started off as a limit. We couldn't do direct substitution, so we cleaned it up until the h, the denominator, went away. Now, can I do direct substitution? Yep. And when you do the direct substitution, that's when the limit gets to go away, because you're actually evaluating that limit. On my next step then, I'll just have the derivative is equal to, I go do my direct substitution, and I end up with just a 2x. And that's my answer right there. Now my question is, does this make sense? Okay, this is different. Let's look at the graph. It's a parabola right here. Just your parent graph. And to say that the derivative is 2x, well, that's not very specific. But you have to understand that the slope of the tangent line is going to change as you ride along the side of this parabola. So the slope of that line is going to be different than the slope of this line, which is going to be different than the slope of, and notice here on this, on a parabola, this is okay to find the derivative. That slope of the tangent line would be that horizontal line because that's a curve, it's not a point. If it was pointy, we'd say no limit on that piece, but notice it's different every place. That means if I wanted to actually find what the derivative is, well, it's going to depend on where you're at on the function. If I was at x equals 2, well then I'd put 2 in here and say, okay, so at x equals 2, the derivative is 4. But at x equals 3, then the derivative would be 6. And at x equals 4, the derivative would be 8. And it would get steeper and steeper and steeper the farther out there that you get. So hopefully that kind of makes sense why your derivative is actually an algebraic expression rather than just a number. All right, another practice one here. I'm going to kind of keep elevating the problem. This one says find the derivative of the function at a particular point. Here's my function. A little fancier. It's a quadratic. Going to have to square it. But so I'm going to start off just like the last problem. I'm going to find the derivative of this function. It's going to end up being an algebraic expression that I can then plug in to see what the derivative would be. Here we go. Nice notation. The derivative is the limit as h approaches 0 of, I'm going to take x plus h and I'm going to plug it in for x. I'm going to end up with a 3. Oops, I don't know why that changed. I'm going to have a 3. And then recall that x plus h squared is going to be x squared plus 2xh plus h squared. And then I'm going to subtract the actual function. Oh, sorry, hang on. I didn't finish writing this. I plugged this in for x squared, right? But I still have that plus 1, so don't forget to do the plus 1, like I just did. Now I'm going to subtract the function, take this whole function and subtract it. Minus 3x squared minus 1. This is all over h. And since it's a limit, my first thought is to go ahead and try direct substitution. It's not going to work. Let's clean this up, see if we can get that h to somehow cancel. Distribute your 3. And let's see, we've got a 3x squared and a negative 3x squared. We've got a plus 1, we've got a minus 1. And I think that's all that's going to cancel. Now what I'm looking at is what's left has to be divided by this h, but everything has to get divided by the h. But it looks like both of these have an h that could divide out. This would go away, and this would turn into a 1. And then I could cross that h off. Now I have the derivative is equal to, I have not yet put 0 in for h, so leave that limit there. Now I'm ready to evaluate the limit. And what that means is now I'm ready to do the direct substitution. If I put 0 in here, that goes away. It looks like my derivative is 6x. It's like the last one. It was a parabola, so the slope of the tangent line is going to change depending on where you're at. Wherever you're at, you'll substitute in for x to see what the slope is at that particular spot. They are specifically asking for the derivative at x equals 2. This is my first answer right here, but the second part I would write like this. The derivative at 2 is equal to 12, and that's the second part of that. going to take it a step further. Could we find the equation of that tangent line? Yeah. Not only do we know that, if we know the slope of it, I bet you we could also figure out the equation of that tangent line. Recall what the graph looked like. It was a 3x squared plus 1. So that's a skinny parabola that's been translated up 1 unit. Looks like that. And at x equals 2, let's say that was right here. Here is the tangent line. And what is the slope of that line? 12, right? At x equals 2, the slope was 12. To write the equation of a line, you need the slope and you need a point. Do you suppose we could figure out what that ordered pair right there is? Well, I know the x value is 2. How do I find the y value for that ordered pair? It just falls on the parabola, right? So the equation of the parabola was 3x squared plus 1. If you plug 2 into the function right here, 2 squared is 4 times 3 is 12 plus 1 is 13. That ordered pair is actually 213. That means I have the slope and I have a point. I could go write the equation. You might do something in your notes so you know where that 13 came from. Maybe let's do this. We plugged 2 in, and I got 3 times 2 squared plus 1. So evaluating the function at 2 got me a 13. So grab that and show where that's coming from. Now I'm going to just do a little bit of Algebra 1 work where I have a point and the slope. You can use point-slope form if you like, or you can use slope-intercept form. I'm going to go ahead and use point-slope form because in calculus you tend to use point-slope form a lot more. Y minus y equals m times x minus x. And then if we wanted to put that in slope-intercept form, and we typically will end up in slope-intercept form, you're just going to distribute to get rid of your parentheses and add the 13 to the other side. That's going to get us a y equals 12x, and then I'm going to have a negative 24 plus 13. That's going to be a negative 11. And this, ladies and gentlemen, is the equation of the tangent line. Pay attention to the directions. Sometimes they're just going to ask you to find the derivative. You just go evaluate the limit, but then sometimes they have you take it the next step. You should have an example then of each of the different things that you're going to have to do on your homework. Good luck.